Okay. Well, welcome everybody to our Solar Banana Bread podcast. And today we're going to go over some frequently asked questions in the vein of Solar 101. We're going to try to stay in the vein of super basic so that anyone could understand. I have to keep this in mind in particular, more than most folks. I tend to be off in tier 3 talking about the details that don't make any sense to anyone. But we're going to try to focus on the basics. I'm going to remind myself that I should be able to explain this to my 9-year-old. He's pretty clever.
Hey, I think if we start the topic simple and then we elaborate, you never know who's listening. There might be some science geeks online.
Right? So, with that said, I'm Schwa Rice. Schwa as in the last part of Joshua, because that's my actual name. I was in a small class growing up with a lot of Joshes. So I'm Schwa, and I always get asked what that's about. So that's what that's about. I've been in the industry for 15 years, providing technical support for off-grid solar and for grid tie solar as well. And I specialize in battery chemistry and solar permitting, and you know, you name it, I've done it. So I'm excited to be here with Wil and with Connor. And Wil's got a presentation for some of the 101 stuff that we're going to go over. So I'll hand the reins over to him and we'll get going.
All right, thanks. My name is Wil Burlin. I'm project manager. I've been working with Schwa for about 15 years as well. I started out in sales and system design and then got moved into the tech support team. And now I make blueprints, plan sets, and help Schwa out with technical calls, mostly fielding the calls and giving him the information. But I'd like to talk about different types of solar systems. We'll get to the 101, and then if you want to elaborate, if anybody's watching, feel free to chime in the comments, and we'll work on those questions in real time. So every house could have different types of solar needs. I think the most common, the simplest, and the cheapest is called a grid tie solar system. This is where the solar panels simply reduce the amount of power your house is pulling from the grid. If you're overproducing, in other words, if your solar is creating more power than your house is using, it stores that power in credits at the utility company by turning your meter backwards. So if you turn your meter backwards while you're at work and pull it forward when you get home, that's how a grid-tied system pencils out. Connor, Schwa, do you have any thoughts on that?
No, I just wanted to mention that I was able to get the slide deck into the interface. So I'm curious if you all are able to also change the slides. That might be easier for you if you want to just click. If you mouse over, does it let you click through the slides?
No.
Okay, that's fine. You can just tell me when you're ready to move on, and I'll manage it then. But yeah, no questions or comments so far.
Okay, cool.
I think the grid tie system is well, it's what everybody does. It's like 90% of solar systems that are installed are just grid tied systems, right? No batteries. No batteries means that the system costs a lot less, right? So it's the make your power bill go away for the cheapest, amount of money. And that's what a grid tied system is. But you always have to mention to people that unless you're talking about grid tie with battery backup, a grid tie only system doesn't work unless the power is up, right? The utility company has to be making power and sending it to your house in order for a grid tie system to work. So that if you had a grid tie only system with no batteries, when the grid goes down, like you have a utility outage, your solar panels turn off and your inverter turns off, because a grid tie only inverter is a synchronizing inverter, meaning that it can't make its own AC waveform, right? It can't take DC power from solar panels and just make 240 AC to send down the line. Like it can only see AC power, sync with an existing AC power source, and push current towards it. So That's my comment on grid tie only, is you have to have utility power and it has to be available in order for a system like that to work.
I get a lot of calls where folks will call me and say, I bought a grid tied system 5 years ago. How come it turns off when the grid goes down? And there's a couple of reasons that I can think of. One is it has to, so it's not sending power on the grid, so your linemen don't get hurt. And two, it's cheaper. You bought a grid tied system simply to get a return on investment and reduce your power bill.
Well, that works for a lot of people.
It does. And if you get past the first hurdle of, well, why would I do that and not have power during a grid outage? My next answer is, well, how often do you have a grid outage? I mean, I personally haven't had one in 6 months, and it only lasted 10 minutes.
Right. Same.
So how could we quantify it this way? If I had bought batteries 5 years ago and I've only had one power outage, was that the best use of my $10,000?
Probably not. Not unless your utility rates were set up in a way that you were being charged like 5 times as much during peak rates, and then you could run on batteries during those times. So you could avoid paying 5 times as much during the peak times of use. So it's hard to say. At a glance, no way. You know what $10,000 will buy you? Like an amazing vacation to Rome. That would be awesome.
No doubt. So yeah, let's circle back to that. When we start talking about NEM, net energy metering agreements, whatever they're called, then yeah, totally. I forgot about that concept. Using batteries to cheat the power company out of their expensive rates is a relatively new concept and definitely not something I cut my teeth on. When I'm trying to justify grid tie, it used to just be, well, it's the cheapest and fastest way to get a return on investment. But you're right. Now the electric company can charge more for their electricity between 4 and 7 o'clock. We can circle back and kind of beat them at their own game by using batteries. Let's flip to the off-grid slide.
Alrighty. There we go.
All right. Well, an off-grid system is a different story altogether. This is great for your off-grid cabin places. When we say off-grid, we mean there's no utility lines out there. Let's say you bought a farm in Texas. There's no utilities and you need power. So an off-grid system is one way to do it. It's got solar panels and an inverter, just like grid tie, but now you're storing all your power in the batteries. There's a couple of more pieces of equipment, charge controller, different kinds of monitoring equipment, but the meat and potatoes, solar panels, inverter, batteries, and a charge controller. One thing about the off-grid system is you're creating your power, from 9 to 3-ish. And if you're at work during that time, that power is basically just keeping your batteries topped off for when you get home. If you live out at your off-grid place, you could be using that power during those peak energy times and use it as it's coming into the batteries, doubling down by using it, as well as keeping your batteries topped off so you have power at night. Schwa, you're a battery guy. Do you want to talk about anything off-grid?
So much about off-grid comes down to the design of the system. I always refer to it as, like nutrition facts, because that's how I look at the ingredients of an off-grid system.
Nice.
The solar panels, we can look at them and say, they're going to make, 1.5 kilowatt hour per day per panel. Okay, so we can get a rough idea of what the panels are going to make just by knowing how many watts they are and how many of them there are and what direction they're facing and at what angle, right? That's our angle and our azimuth. And so if we look at the solar, we can say, yeah, I know how much energy this is going to produce in a day, about, so you look at that, and then you can also look at the batteries in the same way. Batteries are rated in amp hours. And Ohm's law tells us that we can get watt hours by doing the amp hours times the voltage of the system, right? And so we can look at the battery bank and say, well, we know how many amp hours it is. We know how many kilowatt hours that is, so we know how much power we can store. Right now, we know how much power we can store in the batteries, and we know how much power we can make from solar, right? Now we just need to apply that to our loads. And that's the part that's always super unique, because everyone's expectations are different, and that's where you have to find where the rubber meets the road. And sometimes people will come to you and they will say, these are all of the things that I would like to run off the grid. I've done this load evaluation worksheet. And I'm like, hell yeah, good on you. That's great. Quantifying your power usage is like the most important thing about covering all of it when you're designing a battery-based system that's going to do all the heavy lifting, right? You're the power plant manager, right? It's your job to get in and figure out, worst case scenario, what if I was, microwaving a burrito and someone started drying their hair, and I also had the clothes dryer running? What's going to happen? Is that going to be too much, and is it going to trip a breaker? Is it going to automatically turn on a generator that's gonna take over? Ben Mitrovich has a question on, can I power my AC unit all day long on a 10 kW battery? Which is a great question, right? Everybody wants to know how long you can run it. We'll say that if it's 10 kilowatt hours that the battery is, it depends on how many watts your AC unit is, right? Like even a small AC unit, like the smallest one you could find is going to use 1,000 watts. I'd bet you anything.
That's like a window unit.
Or yeah, exactly. The one that you mount in a window, or one of those roll around push ones that you plug in, like 120 volt one, right? If it's one of those 240 air conditioners, you're trying to cool off your whole place, you're talking probably 2,500 watts, right? So let's look at those two scenarios. An air conditioning unit that's 1,000 watts and an air conditioning system that's 2,500 watts, like a 120 unit smaller one and a 240 volt smaller one. So we got 10,000 watt hours in the battery. We're going to assume that it's a lithium battery because that's what everybody's doing now. Now you can discharge those 80% of the way, no problem. Even 90% of the way, no problem. If you really get down to the fine print, they're like, yeah, 80 is better than 90 because you'll get a few more cycles out of it at 80 than at 90. But for the sake of discussion, we'll say what? 10,000 times 0.8 is 8,000. So that's how many watts we could pull out of the batteries if they were fully charged. Sorry, how many watt hours we could pull out of the batteries if they were fully charged. Now, back to our air conditioner units. The one that is using 1,000 watts, we could run for 8 hours. Now, that's assuming that we're not running anything else at all, right? Only this air conditioner unit. And it assumes no losses in the inverter, which there are some, So I would guess 7 hours and change, around 7.5 hours. Of course, if we took that 8,000 watts and we divided it by the larger air conditioner unit of 2,500 watts, it's 3.2 hours. And so assuming the same inefficiencies that we did in the last one, I would say for about 2.8 hours to maybe 3 hours, you could run the larger 240 air conditioner that uses 2,500 watts. So what is that? 3 hours, almost 3 hours, and a little over 7 hours for 1,000 watts versus 2,500 watts. Was that too much detail?
Let's play devil's advocate. If you have a solar system that's big enough to keep that battery charged on the daily anyway, and then you factor in, okay, I want to use my 1,000 watt air conditioner for most of the day when it's hot. If you were just running it off the batteries, let's say you get 7.5 hours or so. It's basically 8 hours derated for some inefficiency. What about the sun coming in from the solar panels that's hitting those batteries at the same time you're using power from the batteries? Wouldn't that be a complete offset?
Yes, it probably would be a complete offset. And I like your thinking, but this is where people can run into a bit of a pitfall. Hang on, my mind went blank all of a sudden. Remind me what I was saying.
You said that you would give me $300 if I stumped you?
Oh,
Right.
I'm good for it.
Okay, so you've got a battery bank that can run an air conditioner for, let's just say, 7 hours. But let's say you've got a 6,000-watt solar array.
Oh, right. And the solar is coming in and offsetting the battery. And then there's a pitfall there where usually that solar is coming in and charging the batteries, right? Because you do have things other than the air conditioner that need to be run, lights and outlets and fridge and freezer and all these other things. So those also need to be run, and they need to be run after the sun goes down. So it's still really important that the batteries get to 100% during the day so that we have it available for use in the evening for cooking and showering and for, your alarm clock and the lights and whatever. Like you need the batteries to be charged. So sometimes what happens is people have their system dialed in and are like, yeah, the solar charges the batteries and then everything works great. And then they start adding in an air conditioner. Right now they're running 1,000 watts worth of air conditioning all day long because it's hot. But then the bottom line is that's 1,000 watts of solar that's not going into the batteries all day. Right. So you'll see this time of year, people are turning on their air conditioners and running them all day while the sun's out, which is great. Make hay while the sun shines. Don't get me wrong. But if the sun goes down and you're starting into the evening at 70% state of charge, you're at a disadvantage, of a significant disadvantage, if you're going into the evening without your batteries being fully charged. And that can happen if you're siphoning too much off the top of what's coming in from solar.
So a real good takeaway from this is your load evaluation is key for designing a perfect system, even though, in my opinion, even if you do the best load evaluation and all this, you still have to pay attention to the sunlight hours that's happening and still be conservative. But you can basically do whatever you want.
Word. All right. Yeah, that was like all I had on off-grid systems, I think, at the moment. Although there's a whole bunch more. I mean, I could go on and on and on. It's probably not 101 relevant stuff.
That's okay. I love it. And I think these are great topics for planting seeds for anybody that might be listening that might not be thinking about this kind of stuff. It's just real good to know. I think one of the most frequent calls we have is someone in the South that wants to go off grid and stay cool. I'm in Texas right now, and it's very hot inside my mom's house. Very, very hot. And she lives on the grid. So I really don't see moving off the grid in the deep South and keeping yourself cool. I think there has to be alternatives, like jumping in the lake or something.
What?
Yeah, I don't want to burst your bubble, but
well, look at Benny's question. So check this out. There are some workarounds, but to Will's point, jumping in the creek is also a really good workaround.
What are some other workarounds? Generator assist.
So check it out. Here's how I like to approach this. If we know that in the summertime we want to run an air conditioner and that air conditioner is, several thousand watts, then we can get in and add in several thousand watts worth of solar panels, right, to the system. And then we can say, well, look, now I can bring in the same amount of power to charge batteries, right? And now I'm making an extra 2,000 watts all day long.
Right.
And so now you're doing 2,000 watts to run your loads, and you're still able to put the same amount of power into batteries. And so you're sizing your solar array up, right? Not for the sake of being able to put more power into the batteries, but for the sake of being able to use power as it's being made. And we're adding in the amount of solar array to match the load capacity that we're looking at. And this way, the system doesn't get out of balance. You're like, I got this 12 panels charging this 2 batteries, right? And then that works good. But then you want to run an air conditioner all day, but only when the sun is out. You're gonna hamstring yourself unless you get in and you go, well, 12 panels and 2 batteries, but I want to run AC all day long and air conditioning all day long when the sun's out. So let's see, 12. All right, so I'll end up with 18 panels. I just did magic math in my head. You'd figure out, how many watts and how, but then you would just add it on. So then you could say, all right, well, look, now I can still put this amount into the batteries, and I've freed up 2,000 watts of production so I could run my air conditioner for as long as the sun's out, right? And that'd be a neat thing that you could set up through the smart load output if you had one of the newer transformerless inverters that had that capability. I believe the Fortress Envy inverter does that, and the Solark inverter does that. Pretty cool.
Hey, we got another comment. B. Trent says, hey guys, just a quick note to let you, Wil and Schwa, know that the small off-grid system that you guys helped with is working as planned. Thank you very much.
No way.
Man, I wish we could get you live on camera and talk about how did we design it so good? Did you do a load evaluation for us? Did one of the sales reps talk you through just general ideas? So, just a quick recap, the load evaluation is a piece of paper with numbers. You can also just do this organically by talking about what you want to do. But one of the system designers would really need to quantify all those things to do the math to calculate how many solar panels and how many batteries you're going to need. Or another approach is just go at it with your budget and buy what you can and see how it works and live with the consequences of it. That's how I started. I'm not being snarky,
No, it makes sense, because at a certain point, it's like, well, look, man, this is my budget, right? And so you can look at a system that's in that budget and say, okay, this is within your budget, right? And now we're back to looking at the nutrition facts. Like, this many solar panels will make this many kilowatt hour a day in the summer, and about half of that in the winter. Right? This battery bank can store this amount of power, of which, 80% of that is usable. This inverter can run loads up to this many watts, but keep in mind, your battery bank, you can only pull this many watt hours from it, right? And so now you're looking at a pile of, this is what I can afford, and this is the amount of power it can make and store. Will that work for you, or won't it?
I get another real common question. There's RV kits for sale on Amazon that have, let's just say, 4 100-watt solar panels, a 40 amp charge controller, and you pick your own battery bank. Let's say you've got 2 or 4 golf cart batteries. And I think a lot of people that are interested in camping and boondocking are looking at sites, and they see this very common system. The price tag is affordable. And then they want to know if that'll run the air conditioner on their camper all day and all night. And man, I'm looking at 4 solar panels. The solar panels we sell today are 400 watts. These RV kits have 4 100-watt panels on them. The systems we sell have 20 or so 400-watt panels at least. And I'm just thinking, there's no way in heck this is going to run an air conditioner on a camper. I'm sorry. And, that's about the amount of solar panels you can fit on a camper. And I think those are appropriate for like watching TV and maybe a refrigerator. I don't know. Lights and entertainment, I call it.
The amount of power that it takes to run an RV air conditioner it's a lot, you know. RV air conditioners are stuck in like the 1980s or the 1970s, like design wise, you know. So they're not power sippers. You know, they use power, and RVs, they typically only power up the air conditioner when you're plugged into shore power. You know, you're not going to be able, there's no 12-volt air conditioners for RVs. You'd have to be plugged into shore power, or you'd have to be one of the rare people who's retrofitted your RV with an inverter. And then the inverter would have to be big enough to run the air conditioner. And then the battery bank would have to be big enough to feed the inverter what it needed. And then, yeah, you could have solar panels feeding the battery bank, but like it's, you know, it would cost an awful lot to get a multi-thousand-watt inverter, you know, fitted into your RV, have the whole thing set up, get your battery bank expanded, and you'd be thousands and thousands of dollars into the thing. Like, I just carry around a Honda EU. I have the 3000 IS, which is it's getting a little bulky for me.
Those are the quiet ones, right? So you don't really disturb your neighbors too bad.
My dad has the EUIS 2000, and it's the one that's like a briefcase design where you could just grab the handle on the top and carry it, and it's still pretty heavy. So he got 2 of those, and he uses the little jumper cable that you jump between them to have 4,000 watts from 2 little briefcase ones. And every time we go camping, he laughs at me because I struggle with the 3,000-watt one that's really heavy.
That's funny. Those Honda EU generators have been kind of like a cult status generator since, the late 90s. They used to say they used them on movie sets or whatever, and pure sine wave completely for your electronics and whatnot. The cats meow. I stayed in an RV at my cousin's RV park a couple of times. I've been there in the wintertime and in the summer. And I got to say, those things must not have any insulation, because whatever temperature it is outside, that's what it is inside until you bust out your climate control.
Barf.
Yeah. So
what did Ben had a question a minute ago?
Yeah.
And just wanted
to put it up on the screen. Per hour, is it by kilowatts? Since we look kilowatt needed power devices.
I love this question. It's good to think about things in terms of per hour. Yeah, because when you look at the amount of solar that you're producing, say you're making 5,000 watts from your solar panels. Okay, so you look at the meter and it says 5,000 watts, and you're like, heck yeah. But what does that mean in terms of like capacity? How much is that over time, right? So that's 5,000 watts per hour that it would be sending, right? So that's 5,000 watt hours that are available for battery charging every hour, right? So here, theoretically, if we had 5,000 watts available and we had 10,000 watts of battery bank and we discharged it, 80% of the way. So there's like 8,000 watts that need to be put back into the batteries. And if we have 5,000 watts available from solar, we're going to be able to recharge the batteries in a couple hours, maybe a little over 2 hours. I think the math would put it maybe a little under 2 hours, but it always takes a little longer than you'd expect.
For anybody that's listening, I wouldn't be intimidated by this. I mean, yes, we're going to talk about it over and over and over. Maybe you'll memorize it, maybe you won't. But part of what we do every day is help people understand these numbers and terminologies. Basically, once you figure out how much power you need, somebody on our team can help you figure out what size solar to use. Schwa brought up
solar Sherpa.
You talked about watt hours,
so you can get to the top of the mountain.
That's right. Somebody can carry you all the way through the process if you let them. You're talking about watts times time. Okay. Like, let's look at this picture of the array in the background. There's 6 columns, 4 high. So that's 24 panels, and they're about 400 watts each. Roughly, just guessing since I don't do math. This is like a 10,000 watt solar array. So if you don't even know what watts are, think about your 100-watt light bulb from the 90s before LEDs. It's really bright. It's 100 watts. And, that's a real bright light. Okay, so if this is 10,000 watts here, allegedly you could run 1,000 of those. I don't even know how to do it. 100 light bulbs in real time. That's about how much power that is. So
right? An array that size would make 36 kilowatt hour a day on average. It'd be a little bit closer to 40 in the summer, but could be as low as like 20 in the winter. It looks from the photo, it kind of looks like there's a little bit of some shading and stuff on it potentially. And so, reminder to everybody that even a small amount of shade on a solar panel makes that panel stop working if it has an optimizer on it. And if it's not an optimizer system, it makes that whole string shut down. You could do this with the shade as small as your hand. You could walk up and go boom over one solar cell, and it could shut down the output of like 8 panels. So shade is the devil when it comes to this stuff.
Placement, right?
Yeah.
So these guys and most people that want to build a simple solar system just have their solar panels on an angle and they're facing south, more or less.
If you're doing a ground mount, you really ought to hit it dead on, right? True south if you're doing a ground mount, because you should be able to pick.
Right. And the whole point of a ground mount, right, is to get it out in the sun and off the roof.
Ben was asking why does it shut down with the shade?
Why does it shut down in the shade? What a cool question. It's to do with how all of the cells inside of a solar panel are wired together in series. Each solar cell is going to make about 1/2 of a volt each. So like a 60 cell solar panel is always going to put out about 30 volts, between 28 and 33. And like a 72 cell solar panel is always going to put out 36 volts or within, a few volts of that. So we've got a predictable amount of voltage coming from the panels.
When you look at the solar panel, you can see those little squares that make a grid. So each one of those is the cell that he's talking about. I'm so blind I can't really count those, but I'd bet there's 60 on each panel. And they're wired together with little wires. You can literally see them right under the glass.
Right.
And it's like, what would you say, putting a whole bunch of AA batteries together would be the closest analogy to how cells are wired?
Yeah. The positive of this cell goes to the negative of the next one, and that one's positive goes to the negative of the next one, and they all go in series. And when you put things together in series, their voltage increases, right? So if you looked at the one solar cell by itself, you would say, cool, what does this do if you put it in the sunshine? And you say, oh, it will make, 0.5 volts at 9 amps. Right. And so now we're going to take put a whole bunch of those in series. Right. So now we're going 0.51 all the way up in series, increasing by a 1/2 volt at a time until we get to 30 volts. And now that's 30 volts at 8 amps. Right. So all the solar cells you see inside of a solar panel behind the glass are all hooked together in series. Positive to negative, positive to negative, positive to negative, positive to negative, all the way through, bringing up the voltage, but maintaining the amperage of a single string. Like each one is 8 amps, but they're all in series, so it stays at 8 amps.
So when you say series, it's like stuffing batteries in a mag light, where the negative is hitting the spring at the back, and the positive would be touching the light bulb. Everything in between is your series connections. So if you had one battery in the middle that was dead or shaded, then that string is dead, right? Because you've interrupted the power from positive to negative.
Yes, exactly. Right? So you put your hand over one cell and its voltage of this just one cell drops to 0, right? But that cell is in the middle of a big long series string, and all of a sudden you've created a black hole in the middle of it.
So we've taken that panel offline by shading just one cell. So on a bigger scale, let's look at 8 of these solar panels just to the left of the people. And let's pretend like we have a string of 8 panels. So you got 4 panels going up the array and 4 coming down. All right. And you've got independent strings. So a string of 8, you've got one string over there to the left of the people, one string by the people, and then one string at the right of the screen. Now, if you shade one of those solar panels, now you've broken that whole string, but you still have 2 strings that are active. Does that make sense?
Right.
Okay, so we're talking about how are we going to branch this conversation into optimizers and microinverters. First, let's understand the original grid-tied inverter just deals with a string. So you have 8 panels tied together. That's string 1. You've got 8 panels tied together, string 2, 8 panels tied together, string 3. And with the first series of inverters that came out with no optimizers and no micros, let's say you had a chimney shading one panel out of string 1 for a couple of hours a day. That string is offline, but the other 2 strings that are not in the shade are working okay, right? And then now we can branch out in the conversation. The next evolution of inverter, I believe they invented the in-phase microinverter, where you've now got a solar inverter on every single solar panel, so that if one panel is shaded, the rest of them in that 8-panel group could still work. Did I explain that right at all?
Yeah. Yeah. The microinverter technology put a small DC to AC inverter at every single solar panel attached onto the racking system and grounded with everything else is, a magic box that turns solar DC into 240 AC. And then you're just channeling together all the 240 AC. It's like 1 amp from each panel, and you collect it into this trunk cable that then ties into an AC breaker, and it breaks it down per panel, where if one panel had an issue or one microinverter had an issue, nobody else can really see it. Everything else continues to work normally. Of course, your monitoring would send you an alert, would send you an email, it would send you a text, however you set up your alerts. Hey, you're having an issue with your system. It's this microinverter. Here's where it is in your array. Here's the last time it reported. This is what the issue is. So problems don't go unnoticed, but the rest of the system continues to work is what I was trying to say.
I want to play devil's advocate for any listeners. I know the answer, but why, if you have one microinverter and panel go offline, how come the other 7 panels can still work? Because it's not series?
Right. Because we're connecting all of the AC output side of the microinverters at the array. Right. So it's already at 240 volts AC coming from each solar panel, and each microinverters can do, it's like 300 watts. So it's like 1.5 amps or something, 1.5 amps at 240 volts AC. And each microinverter is doing its own thing, feeding 240 volts AC all collectively into this trunk cable. That's the 240 AC we send from the array back to our breaker panel, through an AC disconnect into our breaker that we're back feeding solar into.
I like to talk about microinverters as if it's similar to a string of Christmas lights. And when you plug the bulb into the string, that's your microinverter. It's like the trunk cable is like the Christmas light wire.
Yeah, like the one that's twisted around.
Yeah, and it's got a little socket where you can plug something into it. Sometimes a light bulb will burn out on a Christmas light and it'll kill the whole string. So I don't understand.
Old school kind,
right?
The new school kind don't do that. This is the end phase is the new school kind. If
We
one
live in
microinverter
amazing.
burns out, only one microinverter is affected.
So let's say, Schwa, when you first started working here, microinverters were really popular. They were pretty new. I didn't know if I trusted them yet, but now they're pretty much one of my favorites for do-it-yourselfers. They're super easy to install. Contractors love it because it's cookie cutter as you can get. Why do you think they invented optimizers? And let's talk about the evolution from string inverter, the old school, to microinverter, to now we've got this hybrid thing called an optimizer with Solar Edge. What's the difference between that and a microinverter, basically?
Whoa.
I mean, it seems to be the best of both worlds because you have a string inverter, but now you also have optimizers.
Yeah, man, I have no idea.
I never really understood why. Like, why do we need Solar Edge?
Well, so yeah, so the microinverters were great because now we have per panel, monitoring and per panel optimization, but it's happening at 240 volts AC, which means that you're running AC wiring on the roof or all the way out to your array. And at 240 volts, you can end up with some losses and might have to run bigger wire, so we start thinking, well, how can we optimize like the panel output with it before we turn it into AC? Like we still want to utilize a string inverter to save on cost and not have, the inverters all be under the panels. So what can we do? Right. And so they dreamed up these optimizers. They're DC optimizers. And what they are is they're buck boost converters. And so what that means is that, so there's an optimizer. It looks kind of like a microinverter, but it's not. There's one that goes at each panel, and then you plug your panel into the optimizer, and then the optimizers plug into each other, right? So the optimizers, I said buck boost. And what that means is that these optimizers can take the voltage, the DC voltage that's coming from the solar panel, and then it can either raise, boost, or lower, buck, the voltage output from the panel, depending on what the inverter is looking for, right? So like a Solar Edge inverter, the older ones wanted 380 volts, and that's what the inverter commanded. And the newer ones, I believe, are 400 volts even. And so like in the case of Solar Edge, the optimizers are all tasked by power line communication with the inverter. The inverter's telling all of the optimizers, look, I need 400 volts DC, and I need you guys to give it to me. Right. And so then all of the calculations happen within, the inverter, and it communicates with the optimizers. And say that there were, 10 panels, and each panel was putting out 40 volts. I'm just going to try to make it easy on myself. So then if you say, well, there's 40 volts each times 10 panels and optimizers in series, that should be 400 volts, right? So in that case, the optimizers shouldn't have to do anything, right? Because it would be coming in damn close to 400 volts. But what if you only had a string of 8 panels, right? Now you have 40 volts per panel times 8 panels. So that's only 320 volts that we'd be getting from 8 panels. And so the optimizers in this case know, well, we need to be at 400 volts. And so we need to boost the total voltage by 80 volts. And there's 8 panels. So each optimizer needs to boost the panel voltage by 10, right? There's 8 panels, each making 40 volts, which is 320. So the optimizers need to make sure that each panel is making 50 volts, and 50 volts times 8 will get it to the 400 volts, right? So that's That's boosting. That's the optimizers having to say, take the solar panel output voltage and boost it up a little bit so that the inverter sees 400 volts, right? And the opposite would be true if you had 14 panels in at panels and optimizers in a series string, and you'd go, well, now what do we got? 40 volts times 14 panels is, and it's 560 volts. Right now we're 160 volts over what the inverter wants, but that's okay, because just like the optimizers can boost, they can also buck, right? So we need to buck 160 volts across, how many did I say? 14.
14.
So each optimizer would need to buck 11.5 volts from each panel if you had a series string of 14 panels and optimizers, because it would, all by itself, the voltage would be too high. So the buck boost optimizer of a solar edge is designed to say, okay, look, there's 14 optimizers. I need to see 400 volts. Now, each one of you panels is making 40 volts. So you optimizers, none of you can make more than 10 volts if I'm to stay in the realm of where I want to be, or however the calculation works out. So the inverter controls the power optimizers to either raise or lower the voltage output of each solar panel. This is at the panel level to maintain a constant voltage input to the inverter. And being at 400 volts, it's like, I don't know, way more efficient than running at 240 volts AC. So you could run a longer distance with a smaller wire at 400 volts versus 240 volts. And that's why you'll see string inverters on ground mounts. And usually nobody will put microinverters at a ground mount, because then you have to run a bunch of current at 240 volts. And someone like me would go, why didn't you put in a string inverter and run back at 400 volts? You could use wire half the size.
Good point. So a lot of people think, and they were told this, I was told this in the 90s, that DC power is inefficient, and what they're talking about is car batteries. You think about putting an amplifier for your subs in the trunk, and you have to run wire as big as your pinky to go 10 feet. That's 12 volt. Nowadays, our off-grid inverters are 48 volt, so it's a little better. And then what Schwa is saying is these DC inverters are up at 400 volts DC.
For the solar side.
And so a lot of folks can't say, they can't relate to DC being more efficient. But if you put a string inverter 200 feet from your house, it's more efficient to run that DC power from the solar array over to the inverter at the house.
That's word, homie.
Where if you put a microinverter at the array, it's 240 volts AC. And while 240 volts AC is very efficient compared to a 12 volt car battery, the DC string inverters are still more efficient than that. So the higher the voltage, whether it's AC or DC, smaller wire size. Is that right?
Let's do an example. Let's say that you had an array and it was 6,000 watts worth of solar panels. Okay. So I'm going to take 6,000 watts of solar panels and divide it by 240 volts AC. I have 25 amps that I need to send somewhere in the wires, right? Okay. Now let's do the same thing. We're going to go 6,000 watts, and now I'm going to divide it by 400 volts. Now I only have 15 amps that I have to send somewhere. So 15 amps versus 25 amps. I mean, like, it's that big of a difference on the voltage.
And that's, more or less irrelevant if it's AC or DC. For folks to wrap their head around it, you're talking 15 amps versus 40 amps, period. And then maybe AC is a little bit more efficient.
Solar panels have 25-year warranties, Benny. I don't think any microinverter has a 25-year warranty.
They do. The Enphase does now.
Are you kidding me?
Nope.
That's bonkers.
I
know that they were all 5 years, and then at one point, everything in the state of California was required to be 10 years, and then that became the industry standard.
Mm-hmm.
I like 25.
I still think all the string inverters are 10 or less. I don't know about Solar Edge, but yeah, micro inverters, as of a couple of years now, they're 25-year warranty.
Man,
You
go
know,
anyways.
they're not the
Really
cheapest,
kicking
but
ass.
I'm telling you, man, sometimes it's worth it to pay a little bit extra for something like that.
It is.
I can give you some real world examples when we start talking about batteries in a minute. Let's recap though. So we've got string inverter is old school. It runs at high voltage DC. It can't tolerate any shade at all. Well, okay, sorry. You can tolerate a little bit of shade, but your string is dead. So if you have multiple strings and only one is shaded, the inverter still works, but it's not ideal.
No,
String
just say the
inverter,
first thing. Just say
yeah,
the first thing and stick with that.
sure.
Will not tolerate shade flat out. A string inverter without optimizers will only work if you have a ground mount with absolutely zero shade. Maybe a roof mount, but with absolutely zero shading.
So good orientation, nice angle. A string inverter is a simple machine. It's still the cheapest, and it's good for long distance ground mount runs. Then you've got the microinverter, which was the answer to the string inverter. It's a little tiny inverter on every single panel. So you're creating 240 volts at the solar array. It's awesome. It's easy to install, 25-year warranty, but it really doesn't like to travel long distances. A lot of folks want to put microinverters on their ground rack, and it's like, well, if you want to, cool, whatever. You're going to have to buy bigger wires.
That's
I,
not a deal killer for me.
yeah, bigger wires, it's just a little bit more money, and you can write those wires off on your tax credit. So,
Oh,
and then third is, I'm going to call it a hybrid, even though it's not, but it's taking the string inverter technology, it's taking ideas from the microinverters, and it's combining them into a high voltage DC string inverter, perfect for ground mounts with a little bit of shade, and because you can still have the high voltage wire runs. I'm not sure. How come if you shade a panel with an optimizer, it doesn't knock the string out? Those are wired in series.
oh, snap. I was hoping that somebody would ask that question. Well, back to my buck boost optimizers that I was talking about. So the inverter is always talking to the optimizers and saying, okay, I need 400 volts divided by however many panels. I need this many volts out of each one of you to have 400 volts, right? Now, enter shade. So now we have shade. And we'll say for the sake of discussion that we have shade on one panel, like a big ass chunk of one panel, like enough to knock it offline. Okay. So now it's like, imagine it's like a nuclear sub. Because it's an alert because all of a sudden this optimizer over here is putting out zero. So everybody's going to have to scramble to make sure the inverter still gets 400 volts, right? So this thing was contributing 30 volts and now it's making zero. So 30 volts divided by however many optimizers are left. And it ends up being something like now every optimizer out there that's working has to boost by 4 volts in order to still be bringing in 400 volts. So one optimizer drops to zero, and like in real time, the rest of the optimizers are simultaneously boosting the panel voltage to make sure that the inverter always sees 400. So even if one of them drops to zero, the rest of them all boost up just enough to keep it at 400. Did I explain that okay?
Yep,
Sweet.
you sure did. So that's pretty cool. Is it inefficient? I was trained when you're dealing with Solar Edge, so the optimizer systems, to go for the biggest string possible. But now I'm questioning that because if you have 14 panels at 40 volts and you're way over 400, is that a waste of power somehow? Or is it taxing your optimizer too hard?
Theoretically, it's not supposed to. It's not supposed to tax the optimizer too hard.
Would you say it's a better design to shoot for like 450 volts for your, just nominal string voltage so that you're kind of in the pocket already?
Look, the closer you are to the inverter's pocket, the less it's going to have to work at converting it to a different voltage, right? If your string voltage is coming in super close to 400 volts max power, it has to do very little work in order to send it down, thus maximizing its efficiency. The more the thing has to buck or boost, the more, overhead cost there is. I mean, it's a very minute amount. I don't think it's even worth writing home about, but it would, I feel like, a string that comes in at 400 volts max power over time would be more efficient than one that, operated at 500 volts max power and the inverter constantly needed to buck the voltage of every panel output. That's got to generate a little bit of heat in the optimizers in doing so, and heat's the enemy of electronics. So over time, I would say, yeah, that's not my favorite thing.
I think as a designer, my takeaway would be, if I'm on a ground rack and I don't have a lot of shading anyway, design my string to be close to the inverter pocket. If I had a tree that's going to shade 2 or 4 panels as the sun starts to go across the sky, I want to have a longer string. Bear with me. Let's say you have to have 8 panels minimum to activate the inverter, but you're going to have 4 panels shaded at some point during the day. It makes sense to build a string that's 12 panels long, so that even when your 4 panels are shaded, you still got an 8 panel firing up the inverter. And to me, that's the takeaway of why you might want to use an optimizer system to begin with.
I sure do like the optimizer system.
Me too.
It was just really well thought through from an engineering standpoint, and it's a shame that Solar Edge doesn't have better availability of product. If they focus a little bit on the growth of their company, they hit a couple stumbling blocks.
Maybe they'll come back around after they see our podcast. That's cool. We love you, Solar Edge, sometimes.
Yeah, that's a fact.
All right.
Yeah, Solar Edge.
Let's bounce to the next screen and talk about the best of both worlds. All right. So now you got a grid-tied inverter that has battery capability. Basically, when the sun's out, everybody's at work, the system's just cranking along. It's creating power, turning your meter backwards, and creating credits for you to use that night, just like regular. But now your inverter costs a little bit more, and you've added a battery bank to it. So the system cost went up, but now you've got batteries. They can hold you. Let's say you've got some critical loads, is what we like to call them. Critical meaning not necessarily the air conditioner. We're talking fridge, well pump, maybe, if you have a pretty decently shallow well. Fridge, home office, maybe, lights, TV. Your battery capacity is directly related to the money you spend on the batteries. Okay, so Ben was bringing up a 10 kW battery earlier. That's probably the industry standard nowadays. That's a pretty fat battery. Yeah. But I've always considered my critical loads to be the refrigerator first and foremost. A microwave is a killer critical load because it relatively doesn't use a lot of power and you can cook food pretty fast. Lights, of course. Water pump, if possible. Schwa, do you want to talk about some of the advantages of why you would want to have a battery besides the obvious of just keeping your fridge cold during an outage?
Boy, it's such a huge topic.
It's getting bigger too, isn't it? It's not just about keeping the fridge on anymore.
Because it's like now we're looking at both sides, right? Like the off-grid part of what can we do without grid power, right? But we also have to deal with this is what we have for grid power, and this is how much of it we use. And so it's like so many different things to try to bring together, and it kind of messes with the return on investment, because it starts to turn into a perspective thing, right? Like you need to have 20 solar panels to make your power bill be zero, right? Okay, so here's 20 solar panels and the stuff to do 20 solar panels. Now your return on investment calculation is X, right? Now to add on a battery-based inverter and a bunch of batteries is going to push your return on investment out by a lot, in almost all cases. And what do you get out of it? What's the extra meat, and it's your ability to keep your fridge and freezer on when utility power goes out, to still have lights on and outlets for, like you said, you're charging your tablets and your phones and your whatever. You could run your television. You can't get bonkers with stuff. But this is when there is not grid power available, your house still has power. That's the extra return on investment. And it's, it has a price tag.
You can't really expect that to be a return on investment when you're keeping your wife and kids happy. And, at some point it becomes less and less about you crunching that penny into more pennies and into, I'm spending money on something that's cool and it makes me happy. And it's a lot more healthy than spending $20 a day on beer.
Now that's
sorry, I politicized it.
That's okay. You're allowed to. It's our podcast. You can do whatever we want with it.
I'm just proud I don't spend money on beer anymore.
Yeah, me too. Because I used to spend a lot on beer.
Me too.
I spend none. Well, okay, so we have the grid tie battery backup where we're like, look, man, grid power fails, and these are the things that you can do, right? This is where people will get sticker shock, right? You're like, you just write down a list of all the things that you want to back up and you send it over to me. I'll make sure we size up a battery system that'll do it. And then they send it over and you're like, and then you send it over to them and you're like, 80 grand. Hello? I think he hung up on me, cause it's, if you don't understand, then you're just like, yeah, my whole house, I guess, whatever. I want to run everything all the time. How much does that cost? It's don't bother, I tell people, I'm like, yeah, you just write down everything you run in your whole house on the back of a blank check and I will get to work on it.
Yeah. And it's fair that not everybody that plays with electricity every day would understand, the cost involved. Think about, when was the last time you bought any batteries for your flashlight, right? It cost about $15 to load up my mag light. And let's say I spent $15 on that and I just turn it on and walk away from it. It lasts like a day, maybe. So I don't know. I'm quantifying $15 for 1 day of a mag light. Okay. But some other things about grid tie with battery backup. Historically, this is like an off-grid system that has the safety blanket of having the grid power there. So you're running everything off the grid all the time. Power goes down. You've got a bunch of awesome appliances you can run now. Kids are happy. I'm happy. My wife's happy. Now, the way that the electrical company charges for power, it's not the same rate all day long. For whatever reason, in the afternoon when kids get out of school, power skyrockets. I think it's because they know kids are going to go home and play video games, and they're going to jack up the prices and really stick it to you during those hours. You can take a system like this, grid tie with battery backup, store your power all day when everybody's at school and everybody's at work. Kids come home, they want to play games and eat stuff and microwave popcorn. Switch into off-grid mode. Use your power from your batteries while they're sticking it to you with the rates. Just don't pay them during that time. Use it from your own batteries. And then when the rates go back down, switch back over to the grid.
Sticking it to the man.
Every chance.
It has a cool name. Energy arbitrage.
Yes, I love that word.
Seemed like some kind of, I don't know, a solar Robin Hood stealing power from the power company, even though you're not really.
Yeah, you're
not buying it from them when it's most expensive, right? This is the idea that the power company could be like, oh, look, man, it's really hard to keep up with everybody comes home and starts cooking and taking a shower. Like, we just can't keep up. So, power's going to be 4 times as expensive between 4 p.m. and 7 p.m. Sorry, not sorry. Right. And then that's just the way it is. Right. for everybody. Now everybody's going to be paying 4 times as much for power between 4 p.m. and 7 p.m. when they know that's when I'm trying to cook and take a shower. Bastards. The audacity. You know, like they're taking advantage of people. You're supposed to have a system that's strong enough where everybody could take a shower at the same time. What's the matter with you?
You know what's weird about this too is like everything you learned over the past 20 years about Solar 101, like you want your panels facing south, this and that. Now with California NEM, all this is wrong now. Now you can put solar on the west side of your roof where when the sun's in the west in the late afternoon, now that's more profitable than putting them on the south because you're creating power during their expensive rates. It's wild.
Right. The power company will incentivize you to have your panels make more power at the end of the day, right? Like overall, the solar panels they're not going to make as much power if you're not facing them south. So why would you point them any direction other than south unless the power company paid you? They're like, yeah, look, man, we got an idea. We'll support all the people who want to, get home and take a shower and wash their car and cook dinner by having a bunch of people point their solar panels west. We'll do west, and then they'll be cranking power at the very end of the day, and that'll stabilize the system. Now, if only we could have a way to have those people point their panels west and then really screw them over on how much we compensate them for.
Man, I tell you what, the games they play are exhausting.
Right. Because if it's not, power costs more between this time and this time, it's, if you use more than 5,000 watts at a time, it costs this much. And if you're using more than 10,000 watts at a time, it costs this much. And if you breach over this amount, then it puts you into this different tier entirely where it's billed at the following rate structure. And it's impossible to keep up with, right? And I'd mentioned this earlier, I think maybe in the last one, how the power companies are like trying to come up with a more clever way to bill people, based on, well, we know they're going to use more power during these times, so let's charge more for it. And then the inverter engineers are like, well, all right, we're going to make an inverter that, will all of a sudden switch all of your loads over to running on batteries between 4 and 7 p.m. or whenever you program it to. And then you don't have to buy their expensive power. And you're like, aha, idiots. But then they come up with the other ones. They're like, well, if you use more than 5,000 watts, it bumps you into this other tier, right? In come the inverter engineers. They're like, all right, we've come up with this thing. It's called peak load shaving. And we've set it up so that you can't pull more than 5,000 watts from the grid. If you're doing, 10,000 watts of loads, you can pull 5,000 watts from the grid, but not more. It'll pull the other 5,000 watts from batteries, right? So now the inverter, you can program it to never pull more than a given amount from the grid. Aha, sticking it to them again, but then the grid's going to come back. And so it's, it's like ping pong, and it's fun to watch them play.
I didn't understand peak load shaving until you just explained it right then. I thought peak load shaving was essentially beating them at the time of rate usage. I didn't realize you could program the inverter to be that smart so that it only pulls so much from the grid and, manages you. That is just insane to me. As an old dude, I don't typically want computers in my equipment, but I'm starting to see the benefits of all this programming, and computers are better now. I don't know.
I just wish that I understood them better. That's my big shortcoming, is I don't understand. My only shortcoming. I don't understand the zeros and ones, right? I was one of these who grew up in the country and was like, I don't understand firmware or software or hardware.
I'm so lazy that I don't want to learn about it. I don't care about it. But now every day I'm hearing more and more about computers doing stuff. AI, I don't know. Okay, we've been at this about an hour. Do we have any more questions, or should we bounce into some more topics?
We do have a couple questions that have been coming in. depends on how long you guys want to go. We could start queuing those up and answering some folks' questions, or
Another
we've got more
50,
content.
almost another hour, I guess.
I'd rather answer people's questions than continue to just go on about whatever.
Yeah, we could pick this up later.
If they turned out, I want to help out however I can. What do we got?
Yeah, for sure. Yeah. All right. So we've got one from Wes Crenshaw. I can do this entire project, building, wiring, you name it, but I can't find anyone around here who is willing to hook it up for me. That seems to be something they want to do themselves to preserve the market. Any suggestions on this?
Is this a suggestion for trying to get an electrician to do the final connection to utility?
That's what it sounds like.
Yeah.
To me.
Yeah, that is kind of a tricky one, because it seems like everywhere you go, anybody who has anything to do with the solar panel wants you to get a solar panel system from them, and they will install it from you, or for you. And so I feel like sometimes people will get a system and put it in themselves, and then it's who's going to hook it up. And I feel like it's only an electrical service call, right? And any licensed electrician can hook your solar panel system up, to the breaker, right? Like if you've done it yourself, then you hook the solar panels up and you put them on the racking, and you did that to the junction box, and that all the way to the inverter all the way to the disconnect, and the disconnect all the way to the breaker panel. And you're like, I've done all this other stuff. Like, you're telling me I'm not allowed to hook these wires up to this breaker? Like, that seems ridiculous, right? And you might just have to eat it and pay an electrician to come over and do that final connection if that's what's required, And it's something that you could run by the inspector. I mean, there's no shame in, saying, "Hey, I've installed my system and need this final connection to be done by an electrician. Is that right? Or can I go ahead and connect this?" And they might say, "Well, yeah, have us out to do the inspection. And then, once we sign off on it and give you your signed plans, then you're free to connect it." I don't know that would be the case. They might say, "Heck no, techno. Here's a list of electricians in the area that are approved to connect solar systems." So you'd want to know. I like the Mother May I game is my favorite one there.
Yeah, we've worked for most of the same companies: Wholesale Solar, Unbound Solar, Go Green Solar, Gigawatt. All these companies specialize in do-it-yourself kits, and so we're selling these to consumers under the impression that they're going to install these themselves. A lot of them have an electrician buddy. A lot of them can find an electrician just in their area. This is a solar system, but it's not different. It's just regular AC power most of the time. And some electricians are intimidated, but really, once you get down to it, especially if you buy a system from a company like ours, whether it's us or somebody else, there's support, and they teach you how to do this. There's electrical diagrams, things that any electrician could follow. And so while it might be intimidating if they've never done one, it's pretty simple electrical work, in my opinion. Mounting those panels to the roof on this barn here was probably the hardest part of the whole deal. And so if you're construction oriented, you should have a pretty easy time doing a solar system.
The racking is the really intimidating part.
For me, it is. Yeah.
I had that same thing. Like when you're making the electrical connections, you got to be paying close attention to what goes where, but you have a wiring diagram, right? Like we don't have a system that goes out without a wiring diagram, so when it comes down to it, how to hook all of that stuff up, then it comes down to, it's like, yeah, man, look, pay attention. You got to drill holes in your roof, man. Did you have coffee and eat your Wheaties? We got to take some precise measurements here.
Yep. And when you're talking to people that have done it a lot, we can give you some tips and tricks, and it's really just not that intimidating. Whether or not the law will allow you to make that final connection, like Schwa said, that's up to the inspector in your building department, but that's like 15 minutes worth of work. So even if you had to hire the most expensive electrician in town, it can't be real detrimental to you.
Right. There wouldn't be any way they could bill you for more than an hour, and it wouldn't be any material required to do it.
Yeah. So don't be scared.
That sucks, man. Nobody wants to feel discouraged at it.
Yeah, I mean, I think that's what's like so useful about, you know, having that team behind you, like you do when you work with Unbound, is you have that support, you know, to navigate all these different challenges. And like we touched on earlier, right, with like NEM changes, like things move fast and it's hard to keep a beat on everything. But this is stuff that you guys live and breathe, right? So and you can, and you know, I think what's cool about working on the team is like everyone has different specialties too and can fill in the knowledge gaps, right? And you know, all to the service of you know, supporting folks who want to work with us. So we've got two questions that are kind of the same topic, essentially asking, is it possible to start small with a grid tie battery backup system, or moving into a house with a pre-existing grid tie battery backup system? Is there a way to expand that system as you go to meet your needs, or run a parallel system? I guess what are your thoughts about expanding something that already exists?
That's a good question. I mean, I would attack that as two questions. One would be expanding something that already exists is possible. There's a little more to it compared to designing and building an expandable system from the get-go. Schwa, you want to take one of those and I'll do the other one?
Well, I guess so. Which one should I take?
I'll start. Okay. If you want to start small, you can design yourself a grid-tied system with any budget. Obviously, you know, one solar panel is about $300. A micro inverter is a couple of $100. Those are ways to do grid tie. If you want to start a battery backup grid tied system, I would really want you to look at different inverters, consult with as many companies as you can. Call me. I'll talk to you about them. Our company carries Sol Arc. They're from Texas. It's a grid tied inverter. It can have full off grid capability. A real smart way to design an expandable system, in my opinion, is not buy the batteries on day one. Get your good inverter, get as many solar panels as you can afford, and let that grid tie and start to pay for itself, knowing that you can put batteries in at any time. And you can also add more solar panels to it later. So I think my preference here would be a good inverter. You can put in a Sol Arc inverter. I would not get the smallest one. Get a 12K or maybe a 15 and put your investment in that round one with as many solar panels as you can afford, and then drop some batteries into it later and add more solar panels to it later. You move into a house that's got a grid tied system and you want to expand on it and add batteries. Schwa, let me lead you with, let's say they've got an SMA string inverter with 4,000 watts of solar. To me, that's the worst possible scenario to how do I add batteries to a system? Because the string inverter dictates how many panels you can have in a string. It doesn't have a battery input. I mean, what would you do in that situation? Replace the inverter?
I wouldn't replace the inverter if it worked. You know, if I had moved into a place and there was a 4 kilowatt Sunny Boy inverter, and I wanted to add batteries to it, I would say, oh, geez, well, usually these Sunny Boy inverters are grid tie only. So that means they turn off when the grid goes down. But I also know that Sunny Boy designed those inverters to work with their Sunny Island battery-based inverter. And in point of fact, that you can AC couple almost any battery-based inverter to a Sunny Boy, and basically trick it into thinking that the grid is up by sending the output of a battery-based inverter to it. It goes, oh, hey, look, there's 240 volts at 60 hertz. I'm allowed to do that and send power back towards it, but it's not really the grid. it's the output of a battery inverter, but don't tell the panels because it thinks it's the grid, right? We trick it. And the key there is that if you had a 4,000 watt Sunny Boy, you'd need a battery based inverter that was at least 4,000 watts. Preferably it needs to be larger than that. So there's a handful of options, right? You could use a Solar inverter and AC couple. You say, all right, well, I got to get a Solar inverter and a battery, and then I use that to turn my Sunny Boy and all of my solar panels on if the grid goes down.
Brilliant.
Right? The grid goes down and your Solar feeds your Sunny Boy, and your Sunny Boy's on and sending power to your Solar, which is using it to charge batteries and run loads. You can get the same kind of functionality out of a Franklin whole home, which is a similar like battery inverter setup that allows you to do AC coupling. You can also do this with the Fortress Envy inverters, which we also carry.
Yeah, I forgot about all these things that are newer on the market, or at least, not something my previous company sold. Never heard of it.
Right. You used to have to use a dual Magnum or an Outback Radian to AC couple that thing, a dual inverter Magnum or the big 8,000 watt Outback Radian, and a bank of batteries, of course.
So AC coupling is the key word here.
Right. It's the key here. And, I feel like the part about it that sucks is that it's not going to allow you to make any more power from sunshine. It's not going to affect your power bill at all. It's literally just going to provide you with power and stored power when there is no grid power, right? It allows your solar system to stay on and continue functioning however long the grid is down. As long as you have sunshine, you're still putting it in batteries and using it to keep your food cold and all this other stuff.
So based on that, I would say it is safe to say that no matter what size system the house you just bought has on it, we could come up with a solution to add batteries.
Yeah, totally. Yeah,
Awesome.
because I'm able to run all of the circuits that I back up. We laughed about this last time, my $508 power bill. But we also talked about how I have a 30 amp transfer switch and I have a 3,000 watt Honda generator. And I have a 4,000 watt Schneider inverter and one 24 volt Discover battery, right? And I'm only backing up my fridge and freezer and a few lights and outlets. Like, I use a lot of power when the grid is up. I almost was about to say it's cheap. It's not. But when grid goes down, I get it. I can't run everything. So I boiled it down to like 3,000 watts worth of shit that I can run. And that covers keeping food cold and all the lights and outlets that I need, And so your backup needs and requirements can be a lot different than your utility requirements, right? Just because you have 60 panels on your roof to make your power bill zero doesn't mean you need a billion batteries to back up everything you own. You could have 60 solar panels for a healthy power bill and then a modest size battery bank for, a modest amount of critical loads.
That's a good point. Back in the day when we were designing full off-grid systems, and you mentioned this last time, your solar array to battery ratio has to be symbiotic. But now you can do these off-grid systems that grid tie and basically have one tiny battery and 100 solar panels. It's not as important to have a nice ratio anymore. It's more about sizing the battery bank to power what you want it to do. You also said grid power is relatively cheap, and when the utility's on, cool. We got the swimming pool pump, we got the hot tub going, baking a turkey in an electric oven. You got 2 PlayStations going, but we're smart. If the grid goes down, it's like, oh, bummer. Well, let's just go outside and play. It's fine. We don't need to jump in the hot tub. You turn off the PlayStation for a minute, go outside, get some fresh air. It's cool. I'd rather do that than have a gigantic battery bank personally.
Hey, if you're out there and you want to flex and keep all that stuff running, it's 100% doable, and I will help you.
That's right.
Just expensive, and most people are like, "Ha, never mind." That was funny, but every once in a while, somebody's like, "Yeah, you still have my attention." Oh, well, all right. Let's do it.
Well, okay, so historically, before solar and batteries started coming down in price, we have, let's just use my family in Texas as an example. They have the big metal building, the cornhole. They got the house with the barbecue pit in the back. The grid goes down. Grandma's hot. We got to keep the 5-ton air conditioner going. The alternative back then was to use the transfer switch and a 20 kW generator. You're using a generator that has 20,000 watts. It's just guzzling gas, but everybody's climate controlled. The game's still on. You got the metal building out back with the band playing and cornhole and all this. It's fine, but you can't hear the band because the generator is so freaking loud.
Well, you should have put it further away.
I mean,
I'm not about villainizing backup generators. I think they're a badass option to have.
Okay, so how do we combine them all together?
Oh my gosh, combine them all together. Well, it's kind of it just makes it more expensive again, right? Because now you're like, well, now you're going to get batteries and an inverter and a generator, right? Like that's the trifecta. That's like all of the things that you need, right? But yeah, I mean, it adds more cost. The generator wants to be controlled by the inverter, right? We were talking about how all of the things have computers in them now. Now the inverter has the ability to talk to the batteries, and the batteries talk back to the inverter, and the inverter also can talk to the generator as far as just telling it to turn on and turn off, and under which conditions and parameters. So it would be the kind of thing where if you had a 20 kW generator, you would say, well, all right, look, man, I don't want to just be ripping through fuel here. So we look at the battery bank and we say, yeah, you could put 185 amps into a battery bank this size. What's 185 amps at 48 volts? That's 8,800 watts. So you could be putting nearly 10,000 watts into a good sized battery bank from your generator. And the point here is that you could charge your batteries up in a couple hours of running the generator, and then it would turn off and your batteries are full and you continue to have AC power available. And then if the sun comes up and it charges your batteries, good. But if it doesn't, for whatever reason, it's raining, pouring, whatever, your generator turns on automatically to make sure the batteries don't get too low. So, having a generator backup, is the cat's meow. Now, if you're off grid, you have to have a generator, period. If you're off grid with batteries and you don't have a generator, I'm not going to help you till you buy a generator. Call back when you have a generator, and then I will help you. I think it's that critical. When you have the grid available and you have a generator and you have a battery and inverter, that's baller, man. That's flexing. That gives you the ultimate flexibility, to do whatever you need to do, whether there's grid power or not. You want to weld, turn on the generator. Doesn't matter if the grid is up, that's rad.
Can you run your generator backwards through a solar and sell power when the grid is charging twice as much for their electricity?
No.
Nice try, huh? Okay.
I like the idea. That was slick. So yeah, we're coming up on an hour and a half here. I do have one more question that's related to, very relevant to what we're talking about in terms of batteries and off-grid systems. Should you overcharge, or Shane wants to know, should you overcharge your backup batteries in an off-grid system? How and how often?
overcharge your batteries in an off-grid system,
Equalize.
they're asking about flooded batteries, I feel like. And they're asking about equalizing. Is that what it reads like to you?
Yeah.
Rad. All right, cool. So if you're using flooded batteries, you will know because they have caps on the top of them, right? A 6-volt battery is made up of 3 2-volt cells. And so there would be 3 water caps on the top where you could take the caps off and you could see that there's liquid inside, right? Those are flooded batteries. And so we want to get in because they want to be charged at a certain voltage, right? You'll say, oh, yeah, these are Crown CR 430s, and they want you to bring the voltage up to 58.4 volts for a 48-volt system, right? And so we have all of our charging and everything. And if we're monitoring the battery bank like a crazy person, like I am, you would get in and you would look at, the voltage of each battery, and you would go, okay, 6.1, 6.1, 6.1, 6.1. Oh, yeah, they're all the same, right? That's not a battery bank that needs to be equalized. But we're like, over time, you would get in and you would be like, I wonder, the battery bank was charged, a couple hours ago. I got a minute. So we check the voltage and we go, okay, I got my safety glasses, my gloves, got my safety equipment, and here we go. I'm not going to unhook the batteries from each other. You don't have to do that. We're just going to get in and measure battery to battery. And we'll go 6.0, 6.3, 6.1, 6.2, 6.3. And we're like, those ain't all the same. Let's see. And I'll be like, check your specific gravity and we'll see what it looks like, right? The specific gravity is the liquid inside of the batteries it's a sulfuric acid solution, and the strength of the acid solution varies depending on the state of charge. Okay. When the batteries are fully charged, the solution is as acidic as it's going to get. And I think it's about 18 to 21% sulfuric acid solution. When the batteries are fully charged, that's what they are, right? As the batteries discharge, the acid gets weaker and weaker and weaker. Once you fully discharge that battery and it reads 0 volts, that stuff inside is just dirty water. It's not even acidic anymore, right? You charge that battery all the way back up, and now it turns back into a stronger acid. The strength of that acid we can measure with like a refractometer, or more commonly with a float hydrometer, which is one of those little tools you can get at the auto parts store to check the strength of your battery that starts your car. The one like you take the cap off and you suck up some fluid and there's like a little ball and it's either floating in the green or in the yellow or in the red, right? And we get in and we check it. Well, so anyway, over time, these flooded batteries, you're going to find that they drift apart. I'm like, hey, is the specific gravity the same on every cell? And you're like, no. Was the voltage the same on every battery? No. So, okay, cool. We'll do a corrective equalization, right? And so this is a controlled overcharging of flooded batteries, where the overcharging is, well, usually you don't want to overcharge batteries, right? But in this case, the benefit outweighs the risk, right? The battery cells, lead acid battery cells, want you to bring them to 100% regularly. Like you have to get them to 100% regularly, to push that chemical equation all the way, where you have H2SO4 on one side, right? Because if that's when you fully charge it, you're removing the water and lead sulfate from the solution, right? And the water and lead sulfate that becomes a part of the solution as the battery discharges is what starts to build up on your plates as sulfation, right? You might have heard of sulfation. This is lead sulfite and that's in your batteries because you didn't fully charge them, right? That sulfation starts to build up on the plates of the battery like plaque builds up on teeth, right? And then it starts taking away the surface area of the battery, right? That's no good, right? So equalization is our tool to fight against that, right? And so we're going to equalize the battery bank, and generally it's several volts above what absorb is, right? Like if you absorb charge at 58.4 and you're like, 58.4 is how high I bring the battery voltage every day. That's the normal thing. When I equalize, the voltage target is 62 volts even, right? You're like, whoa, that's quite a bit higher than 58.4. And you go, yeah, you wouldn't charge it to this voltage every day. You only charge it to this voltage when the batteries start to get out of sync with each other and they start drifting apart, right? You measure them every once a week and you write it down on a book that's next to your batteries. And you're like, these are the voltages and the gravities of the cells that I tested. And then we can check again the next week and see if they're still the same or if now they're starting to be different. Most people don't have the patience for that. And they're like, yeah, that's great. How about quarterly? I'll equalize once every 3 months and the rest of it is just whatever. I'm like, okay, that's fair. You can equalize quarterly, once every 3 months, and we just assume that it needs it, right? Once every 3 months, we're going to bring the batteries all the way up to a full state of charge with a normal charge cycle, right? You can't just get in and equalize a battery bank that's not fully charged, right? A lead acid battery bank has to be fully charged in order to start an equalization on it at all, right? So we have to be starting out at a perceived 100% and we're going to do our equalization, and that's going to bring the voltage up to 62, and that's going to make the cells are going to bubble, baby. They're going to be bubbling and churning. You're going to be like, whoa, it's like loud. They're kind of like roaring. Is this normal? And I'd be like, yeah, totally. When you're equalizing flooded batteries, they're going to bubble and they're going to churn, and that's what they're supposed to do.
They're going to smell.
Right. It's going to smell like rotten eggs. That's that hydrogen sulfide, and that's what it's supposed to do, And so the equalization, you want to find the manufacturer's specified equalization voltage because they're all a little bit different, somewhere between 61 and 62. I don't think I've ever seen one higher than 62. But I have seen them lower. Some of them are like, yeah, equalization at 60.5. I'm like, oh, that was lower than I expected. So check your battery manufacturing specs for where equalization should be, right? And if you're keeping track, then you want to equalize once you've got more than 0.2 of a volt disparity across any of your cells or any of your batteries. If any of them are further apart than 0.2 of a volt, you probably need to equalize, right? Suffice that you could just equalize once every 3 months. It's really important to make sure that your water levels are correct, a couple days before you equalize, because if you get in and you need to add water, you can't add water to flooded batteries and then immediately equalize them, right? They need a couple of charge cycles to even out the solution inside, right? You just put distilled water in, and now it's distilled water on the top and sulfuric acid solution on the bottom. That's not the time to start equalizing, right? Do this a couple days ahead of time, and then the next day, it's going to slowly cycle up as the sun comes up, churn all that fluid together. And then at the end of that day, when the batteries are fully charged and the liquid's at the right level, we'll go, aha, equalization time, baby. Somebody get me a root beer.
Let me ask a question. If you first started out saying you're going to go around and test each battery and you don't have to disconnect them from their string,
that's cool.
Should you check the water and add water a couple of days before you do that?
Not before you check the voltage of each one. That's just kind of a general thing. You want to check the fluid level, like in particular, a couple days before you're going to need to run an equalization, right? And it might be the case that you look and you're like, yeah, all the fluid levels are fine, so I'm just going to go ahead and do that, right? But if you're like, I need to run an equalization, but I also noticed when I was checking the gravity that the water level's really low, then you would say, all right, well, let's top up the water levels, but then we'll hold off doing equalization until tomorrow after they can charge up.
Gotcha. Well, okay, so let me be devil's advocate. I got 4 flooded batteries. I go to water them. Okay, let's say a couple of the batteries need some water. One of them doesn't need any at all. Okay, now I've got fresh water in my batteries. In that same maintenance trip, now can I check each battery's voltage, or do I
Yeah.
need to give it a couple? You don't have to wait a couple of days for
No,
it.
you don't have to wait to check the battery voltage.
Okay, cool.
No, you don't have to wait to check the battery voltage.
That's
And I
pretty
would say
cool.
that if you have 4 batteries and they're not consuming water equally, that's also a sign that you've got some resistance somewhere that needs to be dealt with, whether it be resistance in the cabling, corrosion, or something to do with like the plates, and maybe it just needs to be equalized or something. But they really should be consuming water at the same rate. And if one battery is consuming more water than the others, then we want to get in and in particular be doing specific gravity checks on the cells of that battery to see how they're reading. That battery could have, like, lost a bunch of its internal resistance, and the lion's share of the charging current is going into that battery. That's why I always have one of those laser thermometers. I got a Harbor Freight. It's like $25, and you could stand there and point it at each battery and make sure they're all the same temperature. You get to a battery that's more than a couple degrees different than the other ones, you better stop what you're doing and figure out why. Same as if it has a different fluid level than the rest.
So you've answered my question and brought up another one. Okay, so flooded lead acid has always been historically one of the most robust and, kind of importantly, the cheapest. For folks on a budget, a flooded lead acid battery bank was the most economic solution, and ironically, they seem to last a long time. Now I don't want to do refractometers anymore. I'm older now. I don't want to get out on my knees and mess around with this water and all this. I want to spend a little bit extra money and get a sealed AGM battery. So that's basically the same battery you're talking about, but they're sealed, maintenance free. What happens inside there? Like, you don't equalize those. How do you know if one of the cells is getting weak, and what's the thumb down with AGMs?
Oh, hang on. I got my alarms going off here. Savvy, no.
The AGM alarm went off. Anytime it's mentioned.
My dog's also.
The dog hates AGMs.
He's trained when he hears it.
I like AGMs for what they are, okay? But just as a rough comparison of a flooded lead acid to an AGM, a flooded lead acid is big lead plates, that are suspended in a jar of sulfuric acid, right? Now, the sulfuric acid interacts with the lead oxide in the plates, and that's where we get our reaction and everything from. Now, when you move to a gel cell battery or an absorbed glass mat battery, which are both two different types of lead acid batteries, they're the sealed lead acid batteries. There's flooded, AGM, and gel cell. And AGM and gel cell are widely known to be acid starved as far as their engineering, right? Meaning that there's only enough battery acid inside of there to allow the reaction to happen as many times as it's supposed to, right? Like 6,000 cycles at 50% depth of discharge, So it's, and in the case of an AGM, you have this sulfuric acid solution at like 18 to 21%, and it is soaked into fiberglass matting, essentially. And then this matting is around the plates. So the plates are in wet fiberglass that's wet with the sulfuric acid solution, but there ain't a lot of it. Like there's enough to soak the fiberglass matting, and then maybe and a few extra drops. That's it, right? And that's part of what makes AGMs so easy to overcharge. You can overcharge an AGM battery relatively easily. They're not just plates sitting in jars of sulfuric acid. They're plates that are coated with, a sulfuric acid soaked material, right? They're easy to, you can cook them. right? And then they don't work right anymore. So that's a problem. Gel cells is kind of a similar thing. They take the sulfuric acid solution, and they get it all around the plates, and then they add in basically Jello, right? And it jellifies the whole thing. Now you have plates that are suspended in sulfuric acid Jello, but there's not a whole lot of sulfuric acid Jello. They don't fill the whole thing up, only enough to allow the battery to do the reaction the 6,000 times. Right? So if you start throwing high current at a gel cell battery, it's just going to straight up bubble the sulfuric acid gel away from the plates and make a dead spot, right? And now you've ruined your battery. So you can't get into a gel cell or an AGM and look at the sulfuric acid. You can't test the gravity and go, yeah, the gravity looks good on these two cells, but it's a little bit low on this one. Right? You can't do that. It's a black box. You can only read the voltage on it, right? So, you can't test the gravity, so you don't really know what's happening in the battery. And, you have to be really careful not to overcharge it, because the AGMs and the gels are not tolerant of overcharging because of their acid-starved design.
Nice.
So it's like, if you know what it's capable of and you're like, okay, got it. Don't overcharge it. Got it. Don't, and you follow, then they're awesome. Right. But they're maybe not twice as much as flooded batteries, but I feel like it's got to be close. Like, they're expensive for what they are. And in today's day and age, at that point, like, the jump from AGMs or gels to lithium iron phosphate is so small that it's like, why would you even go AGMs? If you don't want to deal with flooded batteries, get lithium batteries, because AGMs are, they're more convenient because they're maintenance free, but they're still only 80% round trip efficiency, where all the lithiums are at like 98% efficient at the low end, like 98, 99% efficient. Why would you go with a battery that's only 80% efficient if you have to pay through the nose just because it's a sealed maintenance free battery, when we actually know that, you have to be extra careful to not overcharge them, right? You have to be really careful to not over discharge them, right? Because with a flooded battery, you can get in and say, well, look, I overcharged this by like a lot. What do I do? And I say, pop the caps on those things and check your water levels. You can add distilled water to bring the fluid levels back up to the right place, and then put the caps back on and carry on, right? And you can't do that with those other batteries if you've ruined them. You know what I mean? And like, if you over discharge flooded batteries a bunch and you're like, oh my God, they're really low, and what am I going to do? And now they've lost balance. You're like, that's okay. We're just going to charge the shit out of them, and then we're going to run an equalization. We're going to run an equalization today. We're going to skip tomorrow, and then we're going to do one the next day. We're going to bring them back to life. The Lazarus approach, right? We could do that with flooded batteries. So we have equalizations and all these things where it's like, yeah, man, you want to be hands-on with these things and make them work. Flooded batteries, you can do that. AGMs, you really got to hit the nail on the head. If your AGM batteries start to get out of balance with each other, you just have to live with it. You can't really utilize them.
So the lithium cost has come way down, basically putting AGMs out of business. Is there still any reason to use a flooded battery in an off-grid or grid tie with battery backup system, other than the fact that it's about half the cost of lithium?
If you are like me and you already have a background in lead acid batteries to where you're like, yeah, I know how that stuff works, then there is a big benefit in going with it, because flooded lead acid batteries are still largely affordable, as far as buying energy storage goes. And if you already have that skill set, it's pretty easy to put to work, but I lean that way because I've already gone to the dollar store and bought, turkey basters and plastic basins and things like that, because I've already overfilled my flooded batteries and gone, oh shit, and then it's kind of like, yeah, what are you going to do now? You're going to have to suck fluid out of it with a turkey baster or something like that. And like, if you've gone to the store and you've got all the things and you're like, yeah, man, I got a 5-gallon bucket of baking soda. It was only $15. Like, yeah, flooded batteries are for you, but you got to know that you're going to be out there measuring your voltages and checking your gravity and writing it down on a little whiteboard. And, like it's a project, flooded batteries is a project, and lithium batteries are also a project, right? Flooded batteries, you're in it for checking battery acid, checking voltages, making sure corrosion doesn't build up, these things. With lithium batteries, it's a whole new world, baby. Now we're talking about, did you make sure all those batteries are operating on the same revision of firmware? They won't work together if they have different firmwares. You could look at the serial number and probably figure out if they're running the same firmware, right? Lithium batteries want to have online communication. You're supposed to be able to look at your lithium batteries on your phone, and so then it kind of drags you kicking and screaming from the off-grid world with lead acid batteries and checking battery acid strength into the world of, I understand that firmware is something between hardware and software, but I also need help.
Yeah, I
So
agree.
it's not like lithium is the magic, just get lithium and everything will be fine. There's trade-offs. The batteries that are flooded lead acid require some hands-on what's going on inside of these batteries. And the lithium batteries requires some hands-on, I need to be able to look at the zeros and ones inside of this battery on a computer.
Yeah, I don't even want zeros and ones in my batteries, but I will come around, I think.
I'm a fan.
All right. Well, we're getting close to 2 hours. Do we have any more questions?
I hope so. This is so fun.
I think that's all we have from the chat. But
I had
yeah,
one other thing I wanted to touch on real quick. I
yeah,
had
go
a
ahead.
customer call in today, and this was the third call in 2 weeks of somebody reaching out with a Solarc inverter who was trying to operate either a chop saw or a skill saw and getting an AC overload on their Solarc inverter. And I had this discussion, with each of these folks, and I think I should put together like a write-up or something on it about how the newer inverters like Solarc and the Fortress NV and all of the transformerless inverters. This isn't just a Solarc thing. I'm not picking on anybody here. Transformerless inverters and the way that they handle surge loads in off-grid situations, right? Where you could be replacing an older inverter like an Outback or Schneider's Antrex or Magnum or one of these, with a transformerless inverter, and finding that heavy loads that you used to be able to run easily are now giving you overloads. And the big thing on that is to, look at how you have loads balanced. If you have an inverter, it's going to put out a leg 1 and a leg 2, right? That's our 120, 240. And the idea is that you need all of your loads to be balanced across the 2 legs, right? Because a 12,000 watt transformerless inverter can invert 9,000 watts from batteries, right? So 9,000 watts. I mean, that sounds like a lot, but if you break it down like this, on leg 1, you can run 4,500 watts on leg 1, not more, not a single watt more. I mean, there's a little bit of surge in there, but what people are finding is that where they expected to have a large surge capacity, they had an AC overload fault instead, right? And so the name of the game here is to balance things out, and the universal soft start. This has been something that everybody has been super thrilled about, and there's a handful of them out there. The one that I'm most excited about is the Torque Tamer, Torque Tamer. The what is it? It's the GS11, I think. Anyway, it's a soft starter that it's, you can get soft starts that are like specific for your air conditioner or specific for your well pump or something, but this is like a universal 120 volt AC soft start that's good for up to 20 amps. And baby, this thing gets their chop saw running where it was getting a fault, and then no more. Now they can run their well pump. If it's a 120 well pump, this isn't a 240 device, it's a 120 device. But anything 120 up to 20 amps, and now you can magically run it with a soft starter.
Okay, so you're talking about a 9 kW inverter. You can have 4,500 watts per leg. You plug in a 1,200 watt chop saw, but to get the thing going, it takes 5,000 watts.
Yeah. You get in and start looking at, like it's a motor. And so it has lock rotor amps, and that's the idea that it takes more energy to get the motor up to speed, than it does to keep it there. It takes more energy to get the motor started, and up to full speed from a dead stop than it does to just keep it going. Right. And so while it only uses 1,200 watts continuously, when it's going, that could mean your lock rotor amps or your surge on something like that is easily 2 to 3 times what the continuous is, right? So that's 3,600 watts could be the surge on that. You just have to have a couple extra things on, and you're throwing an AC overload just because the surge on it is high enough. The older inverters with transformers and copper windings would automatically do some load balancing, by having like an auto former in there. And so you could overload and it would do the balancing. And the new transformerless inverters, they rely on the internal switching of the inverter for all like solid state switching kind of stuff. And it's just not fast enough. I think that the soft start really needs to be built into the battery based inverters. Like somebody should have saw this coming, and built that. I think future iterations of transformerless inverters will have this soft start thing built in, because nobody's going to want to have to continually be sending out inverters and be like, don't forget to go to Amazon and buy a couple of Torque Tamer GS11s. You'll need one for each phase. Like, why isn't that built into the inverter? You've got to be kidding me. So somebody's going to come out with that, and whoever does is going to win.
Does that thing wire into your breaker box, or does it plug into the wall?
Dude, it plugs into the wall. It's got like a big old 120 grounded plug on it, and then on the other side is a 120 grounded plug. And inside of it is a bunch of capacitors and printed circuit boards and, fancy stuff.
Okay, so you've got a soft starter plugged in the wall. You plug your chop saw into it. We know the chop saw would exceed the power of the inverter. So you mentioned a capacitor in the soft starter. So that means that the soft starter is like building up energy, and then your lock rotor hits and it delivers that surge to the item.
Yeah.
One blow.
Like the power stored in the electrolytic film capacitors allows the top part to be, filled in by the stored power, right? It's kind of like similar to when I was saying we got a 5,000 watts, all we can use from grid is 5,000 watts. So if we have a 10,000 watt load, 5,000 watts has to come from the grid, and the other 5,000 watts has to come from the inverter.
I love it. We should have a special where we include this with every solar converter we sell.
Yeah, I know. To do so is to admit that the solar converter and all transformerless inverters, again, I don't mean to pick on them. They're just my favorite, so their name keeps coming out of my mouth. But it's a known problem. Surge capacity on transformerless inverters is hamstringing off-grid people who are trying to run power tools and heavy loads. But there is a solution. You don't just have to be like, I don't know, I need a second inverter, I'm screwed.
Yep, that's come up before.
There's answers,
Yeah.
right? But transformerless inverters are so new to the market that people haven't really felt out all the little nooks and crannies of how to make things work. Like, yeah, how do you overcome the lack of surge capacity in a transformerless inverter when you have an off-grid fab shop?
Yep. And what's cool is the people that are finding out these issues and bringing them to the public attention are our customers. It's not the engineers beta shooting their inverters. It's people like us that are like, oh man, I couldn't run my dryer today. The engineers didn't think of it. And I don't know if you've tried lately, but it's hard. You can't even find a transformer based inverter today. I'm not going to say they don't exist, but try to find an Outback inverter, try to find a Magnum inverter. They're just not available in my circles.
Well, and I feel like that's okay. I did prefer them. It's okay that they're gone. Now we have these other inverters. How do we make them work? I've always been the kind of guy who's just like, whatever toys are in the sandbox, that's what I'm playing with. I'm going to go find somebody and ask for cooler toys, just whatever's there. So now we have transformerless inverters. Those are the tools we have to play with. And to make them work, we need to get other cool tools, soft starters. There's a lot of them are the units, they're soft start units designed for RVs, and they are meant for turning on 3 air conditioning units in an RV. So they're like big 60 amp, setups that you can use.
That's cool.
I know, right? All right, I gotta stop going on tangents. You're like, okay, well, we're pretty much out of time, and I'm like, wait, I have another 20-minute thing to cover.
Yeah, let's go another hour.
No,
break some records.
I don't want it.
Connor's got to go
on for 100th episode or something like the
hey, yeah,
5 hour special.
Save something for next week, bro.
Right.
Yeah. Next week, I would like to talk about safety and installer safety. It doesn't come up enough, the different kinds of safety harnesses and anchors that are available. But I do feel like it would be really good content to cover, what safety equipment is available and how to properly use it, where the good resources are, and that, because I don't see people covering that. And I see a lot of customer photos coming in where I'm like, man, that looks great. You didn't use fall protection, did you? This picture of you clearly shows you didn't use fall protection. And I want people to be safe. At one point, I did have somebody fall off of a roof and get bad hurt, and it was no good. So let's don't forget safety.
All right. Tune in next week.
Yeah.
Sounds good. Well, yeah, thanks so much for your time today, Wil and Schwa. It's always, I know I always learn so much from just sitting in on these conversations. And we really appreciate you taking the time to share the knowledge and get the word out.
And I appreciate you running the boards, man.
Yeah, do my best. Yeah, excited for next week where we'll get into some safety tips, and yeah, especially for DIY, that's super important. Keeping yourself safe. And yeah, well, until then, I hope everyone has a great weekend, and we'll talk soon.
Later, dudes.
All right, we got to stay online to let it upload.
Yep.